So hello everyone. I'm Aude Simar from the Université catholique de Louvain in Louvain-la-Neuve, Belgium. I will talk to you about the friction stir mixing to process new composite materials. And I will center my talk on the processing of metals, as I'm more into the metallurgy than into other family of materials. But eventually this could be extended to any kind of material, probably except ceramics, even though people are looking for options there. So before starting, I would like to thank all the people that have contributed here to this work, and some colleagues at UC Louvain, Bruno de Meester, Francis Delaney, Pascal Jacques, and Camille van der Rest, some colleagues from the University of Liège in Belgium also, some people from the CIRIS Research Center in Liège, people from the Université Lille 1, from INSA, Lyon, Eric Mer, Jérôme Adrien, and people from Danish Technical University, and finally from a company called Bang & Olufsen that make speakers. So the problem of making composite materials is that metal-based composite materials is that you need a processing method for putting the reinforcement in contact with the metal. And usually you do that by, or classically, let's say, you're doing that by some liquid state processing, for example, by squeeze casting. Here you put some preform. You put some liquid metal inside and you put pressure, and with this pressure you infiltrate the preform, and you produce things that look like this. So you have here some composite carbon fiber and a magnesium matrix. It's very difficult to control these kind of processes. In particular, here you see, before doing this, we made things like this. You know, you have a lot of defects, problems of control of solidification, problems of wetting of the metal on the fibers, and interface reactions between the metal and the reinforcement. So that's why it's sometimes interesting to produce these materials by powder metallurgy processing route, and for that it's an example here is the production of a copper-based composite with yttrium oxide and with some milling. So you put copper powder, yttrium oxide powder, and with milling, compaction, and sintering, you end up with a compact that has interesting properties. You can also do that by spark plasma sintering or other methods. And by spark plasma sintering, you probably end up with a better density. Here, the authors of this paper, they did it with classical sintering, just putting the material in the oven, and so they end up with a material that has a density very low, only 87% of density. So basically, you have lots of voids in this material, and for the mechanical properties of the material, that's not very desirable. And also you need a long processing time to make such materials, and usually you work with very small samples. So we are looking for other solid state alternatives, ways of making materials that do not pass through the liquid state to have all these solidification and wetting problems, but avoid the powder metallurgy that has the problems that I have mentioned in terms of density, in terms of in terms of the size of the samples. So why not consider solid-state welding processes? Processes that use plastic deformation to join materials. And so we started working quite a long time ago on friction stir welding. Friction stir welding is a welding process that uses a machine that basically looks like a milling machine. And so you have a tool that's put in rotation, and that's composed of a shoulder here, sorry, and of a pin. And once the tool gets down into the material, the pin will penetrate the material and put some plastic deformation and friction, and this will deform the material, mix the materials, and so the two plates will be joined together by this welding process. And then you can continue going ahead in your weld, move forward, so have some advancing speed, and so your joint will be closed. So you will have what we call here a nugget in the center of the weld that has very interesting properties. So what you have in this nugget zone is very large deformations and large temperature that can go up to 80% of the melting temperature or even higher. That brings the material in a dynamically recrystallized condition, and you will have fine grains in this material. So here you see that the base material, so here we are cutting the weld on its side, so the welding direction is coming out of the slide, and so the base material is composed of rather large grains, and when you go in the weld nuggets, you see that you had major plastic deformation and very fine grains. Fine grains are usually associated to very good properties, so it's interesting to look a little more inside this material. So how could we make this material in a larger scale? How could we have the nugget to be actually a material and a larger piece? Well, you can do what's called friction stir processing. So you just use the principle of friction stir welding, but just to make a material locally, use the properties of the nugget to make a material. And so what you do is you have your tool, and you enter your material, and you go for a first round, then you go back next to it, second round, and so on, and then turn over your plate, and you can have a sandwich with nugget material on top, some base material in the middle, and nugget material on the bottom. So you're making a sandwich material without actually joining anything, but just by processing the material. Now we want to make some metal matrix composite. So let's go one step further and put some powder of the reinforcing material inside the little holes here, and so you can make grooves, holes, or any kind of shape to insert some powder, and then you take your tool, you go inside the material, and you mix all that. So you use the large plastic deformation at relatively high temperature, but below the melting temperature of the material, to actually mix your powder into the metal. And so you end up with a metal matrix composite. So what will I talk about today about the things that we have done at the Université catholique de Louvain with our partners about friction stir processing for making composite materials. Well, we've done composites that for mechanical properties reinforcements, and I will talk about nanoytria particle reinforced copper matrix composites. I will talk about the carbon fiber and nanoparticle reinforced magnesium matrix composites. And then I will talk about functional properties improvement, but for confidentiality reasons, I will not be able to give you full details on this, but I will talk quickly about titanium oxide particle aluminum matrix composite with a company Bang & Olufsen that I have already mentioned here, and a multi-layer iron aluminum vinyl for thermoelectric applications. So let's talk about the nanoytria particle reinforced copper matrix composite. So what have we done practically to produce this metal matrix composite, this copper matrix composite, where we have put some copper inside grooves that go all through the material for avoiding that during the process the oxide particles fly away, because it's very light and there is a lot of wind when you're processing. We put a very small cover of copper on top of all that, and then we take our tool, and usually we take tools that are wide in terms of shoulder diameter, because that favors a large process zone, because we don't want here to put to make a very small deformed region. We want to make a much larger deformed region here, the idea being to make a material at a larger scale. Of course, here you only have a small band of material that will be produced. And so we do that many times. Eventually, we pass many times over this region, and with a tool that has some feature here for favoring plastic deformation inside the joint region. So what does the initial powder look like? So the yttrium powder is 3.5 micrometers in specific characteristic size. Now it's made of crystallites that are about 10 nanometers in size, and you see that they tend to cluster a little bit together, so that makes it difficult to separate them during the process. So after 3 passes of friction stir processing, it looks like this. So looking from top to bottom, you see that here on the top the quantity of oxide particles is rather low, and when you get to the bottom you have some clustering that you can see here. I must mention that this is electron probe microanalysis to identify the region. So in green here you have the higher proportion of yttrium oxide, and you see that here at the bottom of the nugget you still have some regions where the homogeneity is not too good, and the homogeneity is improved. You can already see it macroscopically, but when you look at the yttrium oxide distribution, you see that the yttrium oxide distribution, the macroscopic distribution, is much better after 9 passes. So we'll keep on working with samples with 9 passes. So that's quite demanding to put 9 passes, because that means that making one material is still long. And so I was mentioning the advantage of trying to increase the time of processing by this method. Well, here we are a little bit at the limit where it might be interesting to consider other options. But still, let's keep on going with this and look at deeper scale, and see that we have some unfragmented particles that are pretty much the size of the initial yttrium oxide, and some some particles that are fragmented parts of this particle that have been fragmented by the large plastic deformations that you have into the material. And so these are ADX maps to identify these particles as yttrium oxide. So here sorry, the coloring is not identical, but here in green, in blue, you see the yttrium oxide, and here it's in blue. But you see that it's indeed yttrium oxide, so it hasn't vanished from our material. It's well inside. And looking at an even finer scale in the transmission electron microscope, well, you see that these particles are here you see yttrium particles that have been identified by EDX in the transmission electron microscope, and you see that these particles are about 10 nanometer in size, and so that was the crystallite size. So we actually broke the particle and get some pieces of the crystallites that compose this particle. So that's very interesting to see that we can actually reach such sizes. And so we can make nanocomposites with this processing method. Now, you see that after 3 passes, we had still some clustering remaining, and the composite is not sufficiently homogeneous to the level that we were expecting. Now, after 9 passes, what we have been able to see, but of course in the transmission electron microscope you see a very small region, it looks like it's much more homogeneous. So that goes well with our observation at a larger scale. Now, the disappointing thing here is that the volume fraction is still 0.01% of these very small particles. It does have an effect, and when you look at the volume fraction of precipitates in aluminum alloys, for example, you are at very low volume fractions, typically of this order of magnitude, or maybe a little larger, and it does have a huge impact. So when you have nanoparticles, you don't need to have a very large volume fraction to still have an effect, but we're still not to the level that we could hope. But this is very encouraging results. So looking at the grain size, well, the effect of increasing from 3 to 9 passes, well, without yttria, I told you that friction stir processing decreases the grain size. Well, without the yttria particles, you already have a decrease of the grain size, and you can reach 8 microns in grain size. And with the yttria particles, you can even reach smaller grain sizes on 3 microns typically. And so that also improves the mechanical properties of the material, independently of the fact that you have nano-sized particles that will block the movement of dislocations, and so increase the strength of your material. It is also interesting to see that the grain size is decreased by pinning effect of the grain boundaries, and that will also lead to smaller grains and hence potentially higher properties. So, looking at the mechanical properties of these materials, well, we did some tensile tests on these materials. Now I've told you that here is our weld. I've told you that we only do passes on one region of the weld, and we're not doing a full material, a full macroscopic material for these tests, and so we have very small tensile samples, and well, this of course makes it harder to have reproducible results, but still we can work with that. And we also did some rolling of these materials, and I'll detail a little more later why we actually roll these materials. So doing a tensile test on these materials, here are the results that you get. Well, this is the base material, so the copper material. And you see that without powder, you already have an improvement of the mechanical properties and more particularly of the strain hardening of the material. And that is due to the smaller grains that you already obtained by friction stir processing. So it's interesting to already do some friction stir processing on the material without even considering making it a metal matrix composite. And with the yttrium powder, you even have a higher strength and higher strain hardening ability. But as I told you before, the very low volume fraction of oxide particles that were inserted in this material actually give you not that satisfactory results in terms of improvement of the mechanical properties, but we still have an effect, and it's very reproducible. And when you look at the evolution of the plastic slope as a function of the stress, so this is a Cox plot for showing the evolution of the strain hardening ability. You see that these materials have very good a better strain hardening ability than without the oxide powders. And so with Yves Bréchet, we've done some work in the past in aluminum alloys and looking at the effect that this nano precipitates could have on the strain hardening ability. And here we find that indeed the presence of nanoparticles in the material improved the strain hardening ability. And I've told you about the rolling that we did of these materials. We thought that if the strain hardening ability of the material is really good, it might be interesting to push it harder and go to 75% of deformation by rolling. And doing that, well, we have about 50 megapascal difference in yield strength between the material without powder and with powder. So we're actually improving the properties of this material after rolling. Well, of course, it gets very little ductile, and so we probably need to improve the choice that we make here in terms of rolling levels. But to finalize on this subject, I'd like to say that if we can improve the volume fraction of particles that we put in there, and that is our future aim, favoring larger plastic deformation, well, we can really produce copper matrix composites and have improvements in mechanical properties. And improving copper is very interesting because this material is used widely in for its electrical and thermal properties, and if we don't degrade the electrical and thermal properties, which we have already shown to be the case, well then we can have better mechanical properties, and that means that we can improve the quantity of or decrease the quantity of copper that we put here and there for supporting its weight, because it's a very heavy material compared to other materials, and so that has some interesting potential for applications of copper. And here, this is just to show you that, well, fracture, of course, it was not a very ductile material, and that fracture occurs on the large particles. So if we can take out the large particles, well, then, of course, we can improve the properties of that material. So if we can only have very small particles and not the larger ones, well, we'll improve the ductility of the material. So now moving to the carbon fiber nanoparticle carbon nanotubes reinforced magnesium matrix composites. Well, we have a problem about the facts that I mentioned just before, that these materials are produced with putting powders in grooves, and that's not very effective, efficient for making large materials. Well, we are considering options of putting powder through the tool, or other options similar, or just throwing in by projection in front of the tool, or things like that. But in the meantime, what we are doing there is not that efficient for making large-scale materials. So we thought, what would be a good material that we could insert easily in and have something more reproducible in terms of quantity of reinforcement that we put in the material. And so this is where we came to this application, and here it's done on magnesium, but it's extendable to any kind of material. What we did is put some carbon fabric in between two magnesium sheets, and so this carbon fabric that are generally used for polymer-based composites. Well, these fabrics will be broken during the process, and will lead to the production of short fiber composites. So short carbon fiber magnesium composites. So here is the effect of the processing parameters. So I told you that two of the main processing parameters are the advancing speed and the rotational speed. And you see that doing the process that I just mentioned before with the carbon fabric, you see that the process is very sensitive to the processing parameters. If you use too low rotational speed and advancing speed, well, the distribution of fiber will be not too homogeneous. And here, with these parameters, a larger advancing speed and a lower rotational speed, you even have defects that appear, so holes in your material. That's of course not desirable. And so we kept on changing parameters, and at some point we got something that was very homogeneous, and that was with very large rotational speeds, where you see here something that really looks very nice in terms of homogeneity of the metal matrix composite. Also, we had to do successive passes, like we did in the copper application, because after only one pass, well, all the defects, the holes that were present in the overlapping, so the carbon fabric still had some holes in between, and so all that was not completely closed after one pass, so we had to input many passes. And also you see the distribution after one pass is not that good. You still have regions where you only have magnesium matrix. So you see that with this kind of process, you can produce also heterogeneous architectural materials. You can produce materials that have a reinforcement where you want the reinforcement to be. I didn't mention that for the copper material, but you can make a graded material with the yttrium oxide particles on top, and then that would have a better wear resistance at the surface, and then a core that is more ductile. And you can do that here, and here this is a typical picture to show you that we can have a quite sharp interface between the region where you actually have carbon fibers and the region where you only have the base material. And also for the carbon magnesium system, the problem is galvanic corrosion, and so you don't want to have your carbon fibers to be too close to the environment, so it might be interesting to keep them inside the material, so you avoid the problem of contact with the environment. Now, looking at the grain size, I've told you that the grain size definitely decreases when you do friction stir processing. And so this is the size of the grain size in the base material. And then in the friction stir process material, you have recrystallization. And you still have some twins that are present in the material after friction stir processing. So it's not a full recrystallization, and you have significant decrease also in size from 16.4 micron to 10 micron when you actually put the carbon fibers in the material. And we have a volume fraction of carbon fiber that is typically 3.834% in these materials, depending on the parameters that we input. So we are already reaching larger volume fraction, of course, that we had for the nanoparticles, but we are talking about macro or micro particles here. But still, it's probably not sufficient compared to what you can find in volume fractions of carbon fibers in the liquid state process that I showed you at the very beginning, the squeeze casting, where there the volume fraction of carbon fibers is much larger, and hence you have a larger effect of the carbon fibers. But of course, you have defects here. We have defect-free material, and we have a grain refinement in the friction stir composite due to particle stimulation nucleation and grain boundary pinning, similarly to what I mentioned in the copper matrix material. To look a little bit at the 3D shape of this distribution of these carbon fibers, we looked in 3D X-ray tomography. All the images that I showed you before were 2D images, and 2D images that you get from scanning electron microscopy, but that gives you a cross-section of a fiber that can have different orientations. So it's nice for estimating surface fraction that you can eventually extend to volume fractions, but it's also nice to be able to see how they distribute in 3D. And these experiments were performed at INSA Lyon by Jérôme Adrien and Eric Maire. And so we analyzed at Université catholique de Louvain these results and could extract different boxes, let's say, where you can have the fibers here. And so here it's very difficult to see, but because you have a lot of them, but there are fibers that have various orientations in this in this box, and you see that you can see them in 3 dimensions, and so obtain orientations, length, and so forth. So just looking first at the diameter distribution that we obtained by X-ray tomography, and we have the initial fiber diameter was 7 microns. Just to mention that the voxel size was 1.6 microns, so this explains why you shouldn't consider any observation below 2 microns as being really relevant for the measurement that we're doing here. But basically, you have a little bit of fiber breakage, but basically the fibers remain as one fiber. They are just broken on their length. The erosion that you can see here on this scanning electron microscope image, well, you see here that you have a couple of parts that have been eroded from the larger fibers. But basically, you're remaining with larger fibers. Now, the main interesting question is, of course, what is the length of these particles, and that will affect their ability to reinforce the material. And so here we have an effect of the processing parameters on the length distribution. And you see that these are rather short fibers. They are about 3, the ratio of their length to their diameter is about 3, so they're not very long fibers. And as the advancing speed decreases here from 80 millimeters a minute to 300 millimeters a minute, well, you have lower temperatures because you go faster, so you heat for a smaller time, so the temperatures are lower. So you have larger shear stresses, and hence you end up with smaller fibers. And using a shear lag model that I will not detail here, but you can estimate the stresses that these materials have supported, and they are estimated to be about 700 megapascals, so which is very large for the temperature that we reach here. But that gives you just an idea of the kind of conditions that are associated to the very large deformations that we observe here. We don't really believe that these 700 megapascals are really relevant as a value, but that just gives you an idea that we are talking about very large deformation. Some people talk about strain rates and deformation that you can't reach by any other processing method. So, well, this is the fiber length decrease that you see when you have an increase in advancing speed. And also, you see here that we've tested another material which shows which is a stronger matrix. So you have more aluminum in this magnesium matrix, and so it's a stronger material at the basis, and so we actually have also shorter fiber, like when we are using larger advancing speeds. So we can also tune the fiber length by the strength of the matrix, because of course the strength of the matrix has an impact on the behavior after friction stir processing. And here is an interesting thing that we found is at the very beginning, when you start making these materials, well, you start with a carbon fabric, and the carbon fabric has fibers in both directions. They are perpendicular, and so they are made like this. And what we observed by the X-ray tomography, we could analyze all the angles of these particles, and what we saw is actually that these particles, the distribution of angles of this particle is very much centered over one value, so a monomodal distribution compared to the situation where you would expect, starting from things that are perpendicular, you would expect to have a bimodal distribution. So that shows that the process has a huge impact on the distribution of the particle, but also on their angular orientation. And this is a quite complex slide to detail fully, but what this says is that the angular distribution changes, and the angular with the z-axis, which is the axis where we pulled also on the sample, it shows also the direction of processing. And this angle decreases as we are going from left to right of the weld, and here this angle here has a slight decrease here at 1 millimeter from the top of the nugget, and a slight increase at 0.3 or so higher in the nugget. And if you analyze all these results and think of the orientations that are concerned, well, you see that actually what the material does, what the fiber do is follow the material flow. And so the material is turning like this. That has been shown by many models and also from some material flow experiments. And what we see here is that these fibers actually follow this material flow. And so by analyzing this tomography result, we can see that. And so that means that, in addition to being able to produce in addition to being able to produce some metal matrix composite, we can also have insight inside in the process and understand the material flow in this process and how the fibers will orient, will dictate what it has seen in terms of plastic deformation and orientation of this deformation. So here are the mechanical properties, and again, we are talking about low volume fraction of carbon fibers. So the improvement of the material is not sufficient yet to really have a serious improvement in the material. And also the base material is much larger, and that's because that material was strain hardened. It was a rolled material, and we are recrystallizing it. So basically we should start from a recrystallized material to compare with a recrystallized material that would be much lower here. But here we started with this AZ31 material that was rolled for having sheets, and so we are comparing things that are really not comparable. But we could after the processing also roll these sheets and retrieve the capacities, the strength that the material had just due to its strain hardening. And also what you can see here is that the material have the friction stir processing parameters have an impact on the strength that you reach. When you are at 80 millimeters a minute here, so without any carbon fibers, well, you are below a situation where you would be at 300 millimeters a minute. But in each case, you improve the mechanical properties by the strength of the material by putting some carbon fibers in it. Now, this is just to show you again that fracture occurs on the carbon fibers, and so the ductility of the material. If I go back to this slide, well, you see that the ductility of the material is lower when you have the carbon fibers. But yes, well, we are talking about a metal matrix composite, and composites are definitely less ductile than the base materials due to the preferential fracture or decohesion at the interface of the reinforcement. But here, this is a very interesting result that we got very recently because we thought that one of the problems of the magnesium alloys is their very low creep resistance, and in particular the high temperature. Well, medium temperature, because we can't really talk about high temperature when talking about magnesium, but the medium temperature creep, and this is a result that I obtained with some of my students recently on room temperature creep test, showing that the carbon fiber material had a much larger, much better resistance to creep than the material that did not have fibers. And so we are working on doing that at a larger temperature and seeing how the behavior of the creep behavior of the carbon reinforced magnesium composite is doing. Also, lately recently, we've done some tests with carbon nanotubes. So I've told you that having nanoparticles is probably much better in terms of resistance, in terms of strength than having macroscopic particles inserted in the material, and so we had the opportunity to have with the Ceres Research Center in Liège done some papers of carbon nanotubes. So basically we're talking about what they call a Bucky paper, which is a paper that contains carbon nanotubes. So we have the advantage of the carbon fabric that was really practical for making this processing of the carbon fiber, but we have already nanoparticles, so we don't have these much microparticles that have less strengthening abilities. And so the carbon nanotubes were inserted to the carbon nanotubes papers were inserted between the two AZ31 magnesium alloy, and after 3 friction stir processing passes, like we did with the magnesium, where we're not getting very interesting property homogeneity. But after 9 passes, all the carbon nanotubes are homogeneously distributed, and so that's a very promising result for obtaining larger strength, and also the size of the grains is significantly reduced. When we had the fibers, we had 10 microns. Here we are talking about 3 microns. The strength is also increased. We measured the hardness up to now, and the tensile strength is very significantly improved. The problem is that we now have a fragile material, so we have to find a way to solve that. But I suppose in terms of grip that might be interesting. Very briefly, I will talk about some functional properties improvement, and this is a work that we did with the company Bang & Olufsen. They wanted they are making speakers for high quality, very expensive applications, and of course, when we are talking about friction stir processing, it's an expensive process for making materials, so we're not talking about low-cost application, of course. And so this is an interesting application that's more about improving the aesthetics of aluminum alloys. And the grail for designers is actually getting white aluminum, because aluminum is design, and white aluminum sounds really the top of design. So what they wanted to do is insert titanium oxide in an aluminum alloy, and use the light scattering effect of the titanium oxide to give a white appearance to the surface. If you have a lot of the light that is reflected, and that will be improved by the titanium oxide, well, that would have a white appearance instead of a gray appearance. And so they also need to anodize the layer first to obtain that. And so that's a fun application. Unfortunately, I can't say much more about that because there are some confidentiality issues there. But well, you see that you can also improve functional properties. And then one application that I'm working on with one of my PhD students, Camille van der Rest, she's trying to make thermoelectric materials with iron, aluminium, vanadium. And so what is thermoelectricity? It's the direct conversion of the thermal energy under a temperature gradient into electrical energy. So we have a heat source, cold source, and electricity is flowing from the N and P materials. And these materials have to, so you can produce electricity by this thermal gradient. And what's interesting here is that if you have a material that has a high electrical conductivity and a low thermal conductivity, which is of course not very easy to reach, because usually, well, we are talking about copper. Well, this is definitely not the case of copper. So you see that we are talking about very exotic materials, bismuth telluride, expensive, little available, toxic materials. And so thermoelectricity is not profitable for large industrial application usually, because we are talking about materials that are very little available and expensive. So we try to use another material that's based on elements that are more available, like iron and aluminum, and let's say a little more available, like vanadium, but with a lower proportion, so that's okay. And this material has very interesting thermoelectric properties, but I'm not going to talk too much about that. We try to make materials out of that, and so we use the classical processing route like casting. So the rapid cooling condition brought us to crack ingots, and so we controlled that, but that was a hard task, controlling the rapid cooling, and so we went into spark plasma sintering, and there we have very interesting densities. It worked quite well. We also went into reactive spark plasma sintering using the elemental powders. But the problem is the size of the samples, and well, this is a rather expensive process for making a lot of materials. So since I like friction stir processing, I thought, why not try to use friction stir processing here? And so what we did is use a tool that is not exactly a friction stir welding tool, but well, it's quite similar. It's made of tungsten carbide, and this process has been patented because it's also useful for welding iron and aluminum, which has a lot of other applications. And so we welded iron, aluminum, and vanadium, melting the aluminum layer. And after a heat treatment, 48 hours at 1,400 degrees C, well, you can get Fe2 VAL material, a bulk material that's already at a nice plate shape, and so that's quite interesting. But you see that there still is some heterogeneity of composition along the thickness, and that can be exploited also for changing the thermoelectric position from properties from one position to the other. So it might be interesting to also try to exploit this. So, jumping here into some general conclusion, I hope I have convinced you that friction stir processing is interesting to elaborate metal matrix composites or multi-layers, with possibilities of geometrically structuring the materials towards its application, like making architecture materials where you can put the composite where it's interesting to have the composite, and also keep the ductile material where it's interesting to keep it. And then mechanical reinforcement can be sought in addition to new functional properties. So I have told you about aesthetic properties, why not, and thermoelectric properties. Thank you for your attention.